Can we get started?
Yes, Professor.
Yeah. Give me 2 minutes.
Sir, good evening, sir.
Good evening.
Sir, you are in mute, sir. Your voice not.
No. Our speaker sound increase. No. Sir, you are audible, sir. We can
Audible?
start.
Great. Yeah.
Yes.
All right. So let's get started. I'll present my screen. So, so far we have looked at.
Kumar, sir.
Yeah. Is there a question?
Sorry, sir. Here, some mic issue, sir. We are sitting in the conference room. Sorry, sir.
Oh, okay. No issue. So, we have looked at static failure theories. Basically, when a body is subjected to a time invariant load, that means the load does not change with time, how does it fail? Now, when we have dealt with static failure theories, we had an underlying assumption that there are no cracks in the material, right? So whatever failure theories that we have applied does not work when there is a crack in a material. So now we would like to learn what happens if there is a crack in a material. So how do we go about analyzing a structure or a component that has presence of cracks? And that is the science of crack propagation or cracks is called fracture mechanics. And that is something that we will like to do before we move on to fatigue failure, because the presence of crack is an assumption to begin with fatigue failure theories, and hence we will talk about crack propagation and crack extension and fatigue failure. Before we go there, we would like to understand what do we mean by a crack and how does, under what conditions does a crack propagate. Okay. So why people had to start talking about fracture mechanics? Because earlier, before 19th century, particularly until Second World War, most of the designs were based on static failure theory, or based on strength, so to speak. There was fatigue failure theories was there, but there wasn't a significant reasonable understanding of that. But mostly the designs were based on strength, and they were giving higher factors of safety. And only the need for studying the effect of fracture on a fracture based design arose only during or during the Industrial Revolution, particularly in the 19th century, when we have started using metals more and more, right? Steel has become more popular after Industrial Revolution in England, and the iron and steel, and we have been using them extensively for various industrial applications. And as a result, we have been also exposed to several accidents, right? So one of the prominent times during which there is an increased interest in understanding fracture was in the early 19th centuries, that is around 1860 and 1870, primarily because that is when the railway network in Britain was instituted, and then people were traveling using railway networks. And during that time, there were several accidents, and at least 200 people per year were killed in train accidents. So today you might see that this number is pretty small, but imagine a scenario where the mode of public transport was not railways, right? It was just introduced, and the number of people who were commuting is also very less. So to 200 people per year in 1860s could be a huge number. All right. And most of these accidents happened due to derailment of wheels. That means where railway wheel derailment, primarily caused by fracture. That means the wheel would have broken, for example, and that led to the failure, or that led to the accident. So if you look at news items on fracture failures in Britain, on 19th March 1830, the place called Montrose Suspension Bridge. This is a suspension bridge which is having a suspension wires to be your steel metal cables. And at one point of time, there were 700 people were standing on the bridge to watch these boat rides, which were quite popular in Britain. And the suspension bridge collapsed. That means it broke. One of the wires given away, and then the bridge collapsed. And in 1887, it seems to be a very disastrous year for railways in the UK, where within a span of 3-4 months, there were several accidents. So in the 20th April 1887, they have seen the most serious train accident that has happened because of the breakage of the drawbar. And there are other similar accidents. Most of them are associated with failure, a fracture of the components. Another popular failure was observed in these Liberty ship accidents. So there are during Second World War, the Liberty ships were used in Atlantic Ocean to fight Nazi forces, and but in the Britain they were making these ships, but they didn't have enough capacity to make such so many number of ships. So then USA said that okay, we will make them in the US. So out of 2,500 Liberty ships that were made by the USA, at least there were 1,500 instances of brittle fracture. It's a huge number. And 3 of those ships have literally broken into 2 pieces, like what you have seen in Titanic, for example. So why did this happen? They have done a lot of engineering failure analysis and realized that because in a very short period of time, they were required to make so many ships. Typically, the ship hull is made by joints with steel plates, and these joints were riveted joints. And that's how the Britain used to do. But then because they didn't have enough time, the Americans said that, okay, let us not go with the riveting, let us go with welding, because it's going to be stronger and it's going to be faster. But doing welding turned out to be a disastrous decision, because that led to several failures. We will talk about those failures when we are talking about fatigue fracture. So all these failures, whatever happened, are catastrophic failures primarily because of fracture, and all these involved presence of cracks. So for example, if you talk about the commercial aircrafts, right? In commercial aircrafts, you do a periodic inspection that every time the flight is taken, the moment it lands, there will be several inspections that are done. That is, they are called visual inspections. But from time to time, every 3 months or so, they will do a detailed non-destructive evaluation of the flights. Meaning, they will try to understand they will send the ultrasonic waves and I'll try to measure the length of a crack. All these structures will have cracks in them. There is no matter what you do, you cannot produce a product without cracks. There will be cracks, but are these cracks are in such a size that one needs to be worried about? And that is what these periodic inspections will tell you. And if they are not critical, then they will let the flight fly. Otherwise, they will have to do some intervention. And similarly, cracks or crack-like defects in ship structures, bridges, pressure vessels. Everywhere you will have cracks. And hence, also nuclear reactors, the cracks or crack-like defects are a serious concern. So one needs to be worried or keep in mind how to go about designing components when there is a crack that is present in the material. Okay. So in the last class or in the previous classes, we have talked about the stress concentration factor. When there is a geometric constriction, you have a stress concentration, because of which locally there will be very high stress generated, although far away your applied stress is less, right? So that is designated by theoretical stress concentration factor. What does it indicate? It indicates the average load required for the onset of plastic deformation. That means if you apply 100 MPa, you may have a region where the stress concentration is 4 and hence locally the material is experiencing 400 MPa, which is much below the yield strength of the material, much above the yield strength of the material. So one needs to be very careful about it. And this KT, that theoretical stress concentration factor, is limited to structures with known dimensions. You should know, as we have seen in the last class, we know how in order to compute KT, you have to know the dimensions. Depending on the dimensions, the KT may change. And we know if the KT, suppose if you take the case of a elliptic hole, when you make the minor axis dimension C tends to 0, then the KT tends to infinity. That means KT approaches infinity when there is a crack or flaw or inclusion where root radius runs to 0. Right? So if KT is infinity, if you have an elliptic crack or if you have a slit in a material, then the C is essentially 0. Then your stress concentration factor there is 1 plus 2A by C. If C is equal to 0, this should be infinity, which basically means that if I have a paper, if I cut a slit, I don't need to do anything. If I blow some air, the paper should break into pieces, right? But that is not happening, isn't it? Because if infinity means it will immediately reach its fracture strength, but that is not happening, right? So why is that it is not happening is something that we would like to understand. So the failure criteria that we have studied so far, we cannot apply in order to qualify a component to be safe or not because of the presence of the crack. If the crack is present, you cannot apply those failures. So ideally, when you have a crack, you cannot use yield strength or ultimate strength or buckling load based design can't be used. This is our we call strength based design or buckling based design. These are not useful when there are cracks in the material. So one needs to adopt a fracture mechanics based approach, which is essential in order to ensure the safety. And of course, when you are adopting fracture mechanics, so it depends how the material fractures, whether it is a brittle material, whether it is a ductile material, because there is going to be a plasticity involved. In this class, in order to understand the concept, we will only focus on brittle fracture. That means there will be only linear elastic stress field. There is no plastic deformation whatsoever near the crack tip. Okay, that is the assumption. So we are only going to deal with brittle fracture. Okay, so as I told you, if you look at an elliptic crack, ellipsoidal crack, and you are applying a far field stress, yes, the stress concentration factor, the sigma at any position, it depends on the far field stress S times 1 plus 2 root C by rho. The sigma we are talking about as a at the crack tip at the this position. Now rho is the radius of the crack tip. What is the radius of the crack tip? If you would plot or curvature of the crack tip, and if you would plot the stress concentration factor, that is sigma by S, that is on the y-axis, and here you are plotting x by rho, the position. At a given position, what is the stress? And you can see far away it should be equal to sigma y, but near the crack tip it is going to be 7 times the stress concentration factor, depending on the value of C by rho being 3, 2 3s are 6, and then it will be 6 plus 1 is 7. So the stress concentration factor is 7. That means, although a far field you have applied only 100 MPa, here you will see 700 MPa. And that could be much beyond the ultimate strength of the material, and hence you need to be concerned. So we have just learned that it is possible if rho tends to 0, if it is extremely sharp crack, then this guy tends to infinity, isn't it? But infinite stress ahead of the crack tip. If you have a crack tip, this is the crack tip, and you have x position and sigma y. Normally, your theory says that ideal crack, it will have infinite stress like that. But in reality, the crack stress will not be infinite. All right, why is that? So although you are assuming the crack to be mathematically sharp, in reality, you cannot have mathematically sharp crack because the crack radius cannot be less than the size of the atom. So there is a finite crack radius. And as a result, because rho can never be 0, and hence you will have a finite stress concentration factor. Okay, or stress concentration factor. In addition to that, if the material is a ductile material, let us say, then what happens is the head of the crack tip, you will have a plastic deformation. And the equation that we have generated here is assuming purely elastic deformation. But the moment that plasticity comes in, this equation is not valid anymore. And hence the plastic zone that is developed ahead of the crack tip in the case of ductile materials will make the crack blunt. And as a result, you will have a reduced stress concentration, right? Similarly, if you have purely brittle material, so you will have several micro cracks ahead of the crack tip, and those will get affected, those get activated when you are applying the load. So there are different ways that the stress concentration can generate, but unlike the theoretical stress concentration factor that we have estimated to be infinite, in reality it will never be infinite because of these various constraints that we encounter in real materials. Okay, now let us look at this particular scenario. On the left hand side in this figure, on the y-axis you are plotting crack size, on the x-axis as a function of time. Let us say you have a structure whose crack length is some number initially. As the structure is subjected to loading, as a function of time, the crack length is increasing. Okay. So when the crack length is A0 here, then the structure will have some strength. That is what we call the design, the design strength of the material, assuming that there is no crack. But as the crack increases its length, what happens? The material's ability to resist the load decreases, isn't it? The residual strength decreases, right? And let us say you have designed a component whose expected highest service load is this, right? And you have designed the component here. And until from here to here, the failure will not occur because the expected higher service load is here. And once the crack, if the crack length increases beyond, then you will have further reduction in strength. And that is when the failure may occur. And the further reduction in strength happens to the service load. If the reduction in strength is equal to the service load, that is when the failure happens. If it goes beyond that, then the failure takes place. That means as you increase the crack length, the residual strength of the material decreases, isn't it? So in a material, the pre-existing cracks, they grow with the application of the load, and crack length increases with time. As a result, the residual strength reduces with increase in crack size, right? So as a result, when the part is prone to failure from the expected highest service load, even though you have designed it for higher load, but because of the presence of the crack and that got extended, it may not be able to withstand this expected higher service. Is this clear? Whatever I said in this slide. This is something that is very intuitive, isn't it?
Yes, sir.
Okay. Okay, what are the key questions? Okay, if I crack
Sir,
increases.
can you explain more about that residual strength, sir?
So if you have a crack of certain length, then the material will have some strength initially. That is your design strength. Okay. Now, as you are applying the load, right, the crack length increases as a function of time. Let us say the crack length has increased up to here. So you have a component, you have designed the component assuming there is no crack in the material, and hence you have designed it for this strength, right? Now, because the crack has increased, the material has become weaker, isn't it? At this point, the material is only having this much strength, although you have initially designed it to be this. That means you cannot apply a load larger than this value on the material anymore, isn't it? Because its strength is reducing with increase in crack length. I am showing as time, or it also can be seen as crack size, isn't it?
Yes, sir.
Yeah, if your crack length becomes, suppose this is the normal service load. If the crack length becomes this value, then this is the service load that the material, at this value, the strength of the material is this much. That is equal to the service load. If the service load and strength of the material are the same, is that a good scenario?
No, sir.
No. So that is what I mean. As the crack length increases, your material's ability to withstand the load decreases, and hence your design is going to continue to become worse. That means your material is going to give away its ability to withstand the loads. That's what I am trying to say. Okay.
Okay, sir.
Yeah. So now what are the questions? Okay. So what? We know that when the crack length increases, the failure happens. There is nothing special about it because crack length reduces residual strength. So what are the key questions that we can ask? First question is, okay, if you know that there is going to be a crack, and if I know the crack size, do I know what is the residual strength? Okay. For example, if I say that this is my crack size, I have done the NDE and I found that the crack size to be this number. Then if I know the residual strength at that point to be this number, which is much higher than the expected highest service load. What is the meaning of that? The component is never going to experience a service load larger than this. At this particular crack length, your residual strength is higher than the expected service load scenario. And hence, can I say the component is safe or not?
Yes, sir.
Yes, sir.
So, if I know corresponding to a crack size, if I know the residual strength, I can make a decision as to whether I can let the machine or equipment to work, or should I take down the equipment, right? That is a decision that I can take if I know for a given crack size what is the residual strength. So that is the first question. Okay. Now, the second question is, let us say this is my service load, right? Now the question is, if this is the service load, that means this is the load that the material is going to be the component is going to be exposed to. The another question that I can ask is, what is the maximum size of the crack that I can tolerate? That means I know that this is my service load. Then do I know what is the size of the crack up to which I can tolerate? So for example, if my crack size is this, then the service load, the residual strength is this. If I am for sure confident that my component is only going to operate at the service load, I am not going to increase the service load, then I can possibly, depending upon the factor of safety, I can possibly allow this much crack size, right? So that is the question. Can I know what that crack size is that I can allow? And the third question is, okay, now let us say I know what is the critical crack size. So I should ensure that I know my service load. I should ensure that my crack size is not going to go beyond this value, right? Now, when I commissioned the component, I have done the NDT and I found that the maximum crack size is some number, which is much smaller than the critical crack size. Now, when will the structure fail? When this initial crack size, which is found to be much smaller, grow to a size of critical crack size. That is when the structure is going to give away. Now the question is, how long does it take for this initial small crack to grow to a critical crack size? Right? That's an important information as an engineer for us in order to be able to make a decision as to whether I can keep the component in service or not. And then, okay, I'm talking about this thing. So for example, if I have designed a component, for example, if I say I have designed a automobile axle, and the service life of automobile axle is 20 years, let us say. That is the service life that I have given, maximum service life that it can have. I have not given warranty beyond 20 years. Now the question is, what is the maximum size of the crack that can be permitted when structure starts its service life? Meaning, if I am saying that I have to give a life of 20 years, at the beginning of my surface, what is the maximum size of the crack that I can have? If I have a crack larger than that I cannot give you 20 years of service time, because within 20 years it might reach critical crack size, right? And the next question is, how often should the structure be inspected for cracks? Okay, I have inspected the structure for cracks today. And can I, if I am talking about an aircraft, we know all aircrafts will have cracks in them. And now your aircraft company has measured the crack size, and they were considering that the cracks are safe and it can fly. Now, when should I check again for crack size? What is that? Should I do it in 1 month, 3 months? So because in 3 months the crack would have grown, right? And you don't want the crack to be grown to a critical crack size or close to critical crack size in these 3 months. So you need to come up with a service period within how many days I need to do the inspection. Inspection scheduling is something needs to be done. So how do I find out how often should the structure be inspected for cracks? So these are questions that we have, and in order to ensure, these are very important questions. The answers to these questions are extremely important in order to ensure a safe working of a component that you are deploying. So who will answer these questions? The answers to these questions, or some of these questions, can be given by fracture mechanics. So if you adopt a fracture mechanics approach, you can answer some of these questions. And for answering other questions which could not be answered by fracture mechanics, for the other questions, fracture mechanics can show a direction in which you can go in order to find the answer for the other questions. And that is the reason why we need to study fracture mechanics. Okay? Any questions until now? Okay, if there are no further questions, now what do we mean by fracture mechanics? At what scale I need to study about fracture? So there are various scales at which we can understand. One, you can start from atomic scale, meaning you can actually talk about interatomic bond failure. That is also fracture mechanics, but it's a interatomic bond breakage, right? So when does two atoms get separated? Suppose if you are applying only a normal load, how do they get separated? If you apply an oblique load, how do they get separated? Is it the same way, right? And then you have an intermediate level where you talk about crystals and dislocations at that level, right? So individual atoms, individual grains. That's a much higher length scale. So how a crack will propagate through the grains. And then if you are talking about that happens at few micrometers to millimeter scale, and the plasticity happens at few meter scale, because you will homogenize these individual grains and you only talk about macroscopic plastic deformation. And there you are talking about how the crack grows. And then you talk about laboratory scale testing to measure the fracture toughness of the material. But all these should be used at the application level. If you are having an aircraft design, then you need to ensure that the aircraft will not break after so many flights, right? So the fracture mechanics cuts across all these length scales, and a successful design based on fracture mechanics requires knowledge across these domains. So that is why we have studied crystal structure and deformation mechanisms, and we studied what do we mean by plastic deformation. And macroscopically, when I see plastic deformation, how the stress strain curve looks like. All these things we have had a gentle introduction, right? So having this knowledge will enable us understand fracture mechanics based design a little better. Okay. All right. So now whenever we are talking about fracture, we talk about modes of fracture, right? 3 modes of fracture. Sorry. This is what we call opening mode. So if you have a specimen like this, and this is your crack, and this is your crack face, and if your load is applied normal to the crack face, and it opens the crack, this is called mode 1 crack, opening mode. And if your applied load is parallel to the crack face, in the plane of the crack face, then it is called mode 2. This is what we call sliding mode. And this is mode 3, which is called tearing mode, wherein the load is in the, it is not normal to the crack face, but it is in the outer plane direction to the crack surface. So that is what we call tearing mode. So any failure in a component can happen only in mode 1, mode 2, or mode 3, or a combination of mode 1, mode 2, mode 3. Okay, depending upon the type of loading. So now let us do a very interesting experiment in order to understand fracture mechanics. This is what we call a Griffith's experiment. So Griffith is called father of fracture mechanics. Okay, so you have here he did an experiment on a brittle material. Strictly speaking, it is more precisely speaking, it is he did an experiment on a glass plate. Okay, so he has a brittle material which is unstretched in this configuration, and then he took that guy and then he stretched the material. That means he deformed the material and then he fixed it. So that means you take a material and deformed it and then fix the ends. That is the meaning of that. After deforming, you are not letting it move anymore. The ends cannot move now. And then what he did was, he took a knife and created a crack at the center. Like that. What happens then? Then you create a crack at the center. What happens?
It will start to grow actually.
Not necessarily all the time. You have, we will do this experiment in the class now, and then you will realize what would happen.
There
So you
will
have
be some stress concentration.
You have created the crack. Now let us try to understand what happens when you are loaded the system. There is some strain energy that is stored in the material. Do you agree?
Yes.
Right?
Yes.
And when you have created the crack, then some amount of energy which is stored in the material should be released in order to create 2 new surfaces, because it's a crack and the energy should be released to create these 2 new surfaces. Do you agree?
Isn't it the energy should be consumed to create a new surface? Or
That consumption is coming from the stored energy. The moment you create a crack, right? You have created a slit. That slit is formed by consuming the strain energy. The strain energy gets released.
Okay.
The stored energy gets released, and that is forming these 2 new surfaces. Okay. Is that clear?
Yeah.
Yeah. So this is Alan Arnold Griffith. So now, where will the energy come from? The energy the energy that is getting released to create these 2 new surfaces will come from the entire plate. But for the simplicity, for the sake of argument, we assume that the energy is coming from these 2 triangles, whose base is 2a and height is lambda times 2a. Okay. So this is the experiment. Take a sheet. So now we can take a paper, apply a force, you stretch it and then hold the grips. What is the meaning of that? You apply. So if I am taking this fellow, this is the paper, right? I am applying some load. I have applied certain load, but it is not flat enough. So I ensure that it is flat enough. After applying the load, hold it. What do you mean by holding it? You should not be moving the grips. That means these ends cannot move anymore. It should be at that scenario. Now use a knife to cut a slit. So while holding, you ask your friend or someone close by to cut a slit in the center. Okay. And the length of the crack is to be ensured is to be small. If you cut a small crack, nothing will happen. Right? Can you do some, can some of you in the who are sitting in the classroom, maybe 2 people can try to do this experiment. You take a paper and stretch it a little bit and hold it and ask someone else to come and make a slit in the center. All right? Nothing will happen if the slit length is smaller. But as you continue to increase the length of the slit, at certain length of this crack, without further help from knife, you don't need to cut further, the crack will grow. The crack extends. Right? You can do this experiment. Now the questions are the following. What is the critical crack length at which the crack advances on its own without any further help? And can I change this critical crack length for a given material? If you are taking a material, can I change a critical crack length? Also, if you initially have stretched it, no? If you have stretched it to x displacement and held it, or x plus 2 instead of x, if you stretch it to 2x displacement and held it, is it going to influence the critical crack length? So these are the questions that we asked, right? So now we need to understand surface energy as we have discussed. Like surface tension in liquids, solids possess something called surface energy. Basically in a solid, what happens? All the atoms in the bulk, in the center of the material are surrounded by a similar environment. Whereas on the surface, only the atoms of the solid belonging below the top layer will be offering bond strength, bond resistance to the top layer, but there is nothing above the top layer. So that means the atoms at the free surface and few layers below the free surface, there is only bonding force from beneath and nothing or very little from above. As a result, what happens is the surface layers experience strain, the surface layers deform. And the deformation of the surface atoms is what we call surface energy. And what Griffith said was, the crack in a material advances when the released energy, right, exceeds the energy required to create 2 new surfaces. So you have talked about when you are creating a slit, some amount of energy is released, isn't it? And when that released energy exceeds the energy required to create 2 new surfaces, that is when crack propagates. Otherwise, the crack will not advance. Is that clear?
So the energy is very less so that the crack propagates.
So when you are creating a small slit, right, only small amount of energy is released, and that is exactly sufficient for creating those 2 new surfaces, right? If the crack length you have cut is larger, the amount of released energy is more than the already created slit. So then what will happen? The additional energy will cause the crack to grow. That is what it is saying. Okay. That's basically the incremental energy released is what we are talking about. So the total energy release, suppose if you are cutting a crack of length 2a, a slit of length 2a, the total energy release will be strain energy density times volume, out of plane thickness to be unity, then the total volume of the triangles times sigma square by 2e. Sigma square by 2e is your strain energy. So there are 2 triangles, half base into height into out of plane thickness is b. Right, so assuming it to be rectangular cross section. The sigma square by 2e. So this will give you 2 lambda a square b sigma square by e. Let us assume, for without loss of generality, you can assume lambda to be pi by 2. Then typically experiments have shown to be lambda is close to pi by 2. So your energy release, total energy release is pi a square b sigma square by e. That is the total energy released. Right? Now if gamma is the surface energy per unit area of one surface, then 2 times the length of the surface is 2a, outer plane width is b. So this is the area times gamma is surface energy per unit area. So this is the energy required for creation of one surface, but when you create a slit, you create 2 surfaces. So energy required for surface energy required for creation of the surface is 4a b gamma, where gamma is the surface energy. Now, if you would plot this energy released, total energy released and surface energy, you will see that the surface energy increases linearly with A, because as a function of A, that is crack length, it is linear relation. Whereas here it is a parabolic relation. So this guy is surface energy and this guy is your energy released. And you will see that, what did Griffith say? The incremental energy release. Suppose if you have a crack of certain length, and now if you increase the length by some amount, then there is an increase in there is a incremental surface energy release, right? For that small increase in crack length. If that incremental surface energy release is greater than the surface energy required at that instance, that is when failure happens. So what do you mean by incremental surface energy? The derivative of this guy, dER by dA, that is this guy, right? And up to here, from here to here, the slope is less than ES, because this line is parallel to ES. That is where until here, you don't have the incremental surface energy, so incremental energy released is less than the surface energy created. And beyond that, dER by this slope is larger than this value, right? ES value. That is when crack propagates. So that is why this is what we call critical crack length. And if you have a crack of initial crack of A0, then until A0 becomes AC, the crack will not propagate. And after that, the crack propagates. Okay. So if your dER by dA is greater than dES by dA, that is the slope of this line, right? That means you plug in those equations, and then what happens is your critical crack length should be less than or equal to 2E gamma by pi sigma square. E is the elastic modulus, gamma is surface energy, sigma is the applied load. Sigma is stress, that means this is the applied uniaxial stress. So your critical crack length depends on surface energy is a material property, elastic modulus is a material property, but sigma is the applied load. So if you apply a larger load, then the critical crack length will be smaller. At a small crack length, it will catastrophically propagate. And the maximum stress to advance a crack of length A, if you know the crack to be of length A0, then this guy will withstand, it will not be propagating until the applied stress is less than this value, 2E gamma by pi A. If this value is larger than 2E gamma by pi A, applied stress, then the crack will propagate. That's what this equation tells you, right? So now with an advancing crack, the strain, and we know that the strain energy in the component can either decrease or increase. We will see how it can increase. However, the stiffness of the component decreases. And now, depending upon the boundary condition, the point of application of load may move or may not move. That means if you have fixed boundary, then the boundaries will not move. Okay. Now, the work is done on the component by the forces if the points move. Otherwise, energy is consumed, and then energy is consumed to create 2 new surfaces. This is something that we know. Now we will calculate something called energy release rate. That means what is the energy released per unit crack length? That is dER by dA, what we have calculated there. That is what we call energy release rate, or it is given a name called a symbol called G. In the honor of Griffith, it is called energy release rate is represented by G. How much it tells you how much energy is released when a crack advances. So energy release rate per unit increase in crack area. Now let us consider an incremental increase in the crack area to be delta A. That means initially you have some crack and then you have extended the crack by some amount. Because of that, the crack area has increased by delta A. And an incremental external work that is done to create this crack extension. So in order to create the crack extension, you have to do some external work. You need to apply a load to create the crack extension, or you need to do some work. So that incremental work is delta Wxt, right? And as a result, the change in strain energy of the body is delta U. If it is positive, then it is called increasing, and it is negative, that is decreasing. So the available energy is energy release rate times delta A provides the energy balance. So you can say that G times delta A is equal to external work. This is the energy per unit area times area. So it will be energy is equal to external work minus increase in internal energy or change in internal energy. And now if you divide everything by delta A, and in the limit delta A tends to 0, you get D is the energy release rate is equal to minus D by dA, U minus W external minus symbol, where U is the potential energy, strain energy, minus W is the work, external work. So this is what we call potential energy. Strain energy minus external work is called potential energy, that is represented by pi. So energy release rate is now given by energy release rate G is equal to minus of d pi by dA, where A is the crack area, not like crack area. So now the energy is available from the system if the potential energy decreases. So for the crack to energy is to release, right, to be positive, this quantity to be positive, this d pi by dA should be negative, isn't it? When will this be negative? Only when pi starts decreasing, right? Only when the potential energy decreases, that is when the crack extension happens. Otherwise, the crack extension does not happen. Now, let us assume a plate of uniform thickness B. Then G can be written as minus 1 by B d pi by dA. Otherwise, that means this dA is written B times dA, where dA is the small crack length. Now, let us take the example of a DCB specimen. DCB specimen is double cantilever beam specimen. Do you know how it looks like? DCB specimen? Okay, it's not drawn. I just wanted to know how many of you know how the double cantilever beam specimen look like? Or you don't know? You have to say yes or no.
No, sir.
No, sir.
No, sir.
Sir, you
No, sir.
let
Then-
it slip in between actually.
Why is it taking so long to answer? Okay, let me move to my a double cantilever beam specimen looks something like this. So initially you have this is material 1 or material 2, or is it same material 1, but it's an interface. This is the interface. Now if you apply a load, let us say there is a crack here, then if you apply the load, the crack gets opened, and that is how this deforms. This is what we call double cantilever beam, because this is one cantilever, this is another cantilever. Okay. Now let us say in this double cantilever beam specimen, let us say the displacement U is equal to, written as compliance times load. What is compliance? Opposite of stiffness, right? Compliance is 1 by stiffness K, right? So normally, you know, F is equal to Kx, right? Force is equal to stiffness times displacement. So X is equal to 1 by K times F. That is C times F. So displacement is equal to compliance times force applied. So here this is displacement, this is compliance, and this is force. Okay. Now let us say, take a scenario, we have a constant load applied. That means P is equal to constant. Then the strain energy, so this is a linear elastic material. So P versus displacement will give you a straight line, isn't it? If it is a linear elastic material. So the strain energy can be written as half P times U. Can I do that? Strain energy is the area under this curve. Can I do that or not?
Yes, sir.
And now
Yes.
W external work, if I am applying a load P, because of that P, there is a displacement U. Right? Force times displacement is your work done. Isn't it? Now the strain energy release rate is given as minus 1 by B d pi by dA, where A is the crack length. Right? What is potential energy? U minus W external. Isn't it? So that is equal to half Pu minus Pu. Isn't it? So that means your potential energy is minus 1 by 2 Pu. Do you agree?
Yes, sir. Yes, sir.
So now G is equal to minus 1 by B d pi by dA, that is equal to 1 by B d by dA of Pu. Correct? I know that we are applying a constant
Half.
load, right?
Half
And
PU,
2B.
right?
Half PU.
Yeah, 2B. So we are up, P is constant, right? P is constant means P can be taken out. Then that means P by 2B du by dA. Correct? But we have written that U is equal to Cp. That implies I can write U is equal to Cp. That is equal to P by 2B d by dA of Cp. Again, we know this is constant, so I can take this guy out. So this will become P square by 2B dC by dA. That is your energy release rate. Right? Where C is your compliance of the material. Right? Now, this is when you are having a fixed load or fixed load. The load is fixed and the displacement is changing. As opposed to that, if you have a fixed grip, that means U is equal to 0, but P is changing. Or U is constant, not 0, and P is changing. Then the potential energy is what? U is not changing, right? U is constant. Displacement is 0, or displacement is constant. So
dP
then,
by dA.
no,
1 by
U minus W external. If the grip is not moving, what will be the work done? 0, no? If the grip is not moving, this is fixed grip, isn't it? The body is deformed and it has made a displacement of U, and at that instance it is fixed. That means this guy is not moving. So there is no work done. Even if you create a slit, the work done will be 0 and it will be 1/2 Pu. That is your potential energy. So G is equal to minus 1 by B, 1 by 2B d by dA of Pu. And what we know, U is constant. So that means minus U can be taken out, 2B d by dA of P. But what do you know? U is equal to Cp. So P can be written as U by C, isn't it? Yes or no?
Yes, sir.
Yes, sir.
So that is equal to minus u by 2b d by dA of u by c. And u is constant, isn't it? But the compliance of the material or the stiffness of the material changes as a function of crack length. So I can take u outside, minus u square by 2b d by dA of 1 by c or dc by dA. Sorry, sir. Not
D by D.
d by dA of 1 by c. That is nothing but minus u square by 2b minus 1 by c square into dc by dA. Isn't it? Chain rule of differentiation. All of you agree with that or not?
Yep.
Yes.
Yeah. And now I know u is equal to Cp. So in this u, I can plug in my minus into minus became plus. U is Cp, that is c square p square by 2b times 1 by c square dc by dA. C square gets cancelled. That is p square by 2b. Whether you are applying grip, fixed grip or fixed load, your G is p square by 2b into dc by dA. Right? Now, if you take a double cantilever beam specimen, like I have shown you, if you take single cantilever, what is the displacement? This u. Let us say the length of the cantilever is L, elastic modulus is E, moment of inertia is I, and applied load is P. So what is the displacement?
PLQ by 3.
But now you have to be careful when you are doing the double cantilever beam. This is the crack length, right? And it is as if it is fixed here. That is what it means. The boundary conditions are, it is as if it is fixed here. It is what it is doing. So u is equal to WL cube by 3EI. L will be equal to crack length, isn't it? Because after that you need to grow the crack. In order to grow the crack, you need to apply more load. But up to that it will be acting like a fixed end, and then over the crack, whatever crack is already existing, that will freely move up, isn't it? It is like this. You carefully look at the experiment that I am showing you here. I have created a crack of certain length. Can you see my screen?
Yes, sir.
So now if I am applying a load like that, right? Now everywhere here, in this part, the material is intact. So there is no deformation, there is no displacement that is happening. Now if I am pulling, it is behaving as if this end is the fixed end, isn't it? This is my fixed end, and then the cantilever load I can apply, and the length of the beam is like my crack length. This is my crack length. That is my crack length. You can see that? So,
Yes, sir.
yeah, so I can write my U is equal to, for a double cantilever beam, on the top PA cube by 3EI, but at the bottom also it is same, right? So the total displacement will be 2 PA cube by 3EI. And what is compliance? Compliance is equal to U by P, that is equal to 2 PA cube by 3EI times 1 by P. P gets cancelled, right? So what you have? 2A cube by 3EI. Now you have a specimen with out of plane thickness B, and let us say the cantilever has this to be H, right? Then if that is H, the moment of inertia will be BH cube by 12. Do you agree? So your compliance will be 2A cube by 3E. I is B times H cube by 12. So it will go there, and this is 4, that is 8a cube by EBH cube. That is your compliance. So what is your dC by dA then? dC by dA is equal to 8 into 3a square by EBH cube. That is 24a square by EBH cube. So the energy release rate for the cantilever is what is that we have computed? Energy release P square by 2b into dC by dA. P square by 2b into dC by dA, that is P square by 2b into 24a square by EBH cube, that is nothing but this 12 P square a square by EB square H cube. That is your energy release rate. And this is also called mode 1 energy release rate because the load is applied normal to the crack surface. Okay. Now, let me give you a problem and then let us see if you are able to compute this. Yeah. So this is the problem. Determine the critical energy release rate of a DCP specimen loaded in tensile testing machine. The thickness of the specimen is 30 mm. Depth of each cantilever is, thickness means the outer plane thickness, that is capital B. And depth of each cantilever is 12 mm, that means H is 12 mm. And crack length, that is A, is 50 mm. It is made of steel with modulus of 207 GPa. And crack is about to propagate at 15,405 Newton pulling load. That means the crack will propagate when this GI, the energy release rate, becomes equal to critical energy release rate. What he is saying is when I apply the load to be this much, that is when the crack propagates. That means whatever G that you are calculating, that is what is called critical energy release rate. Okay. Can you please do the calculation?
Sir, 22.12 Newton per mm square.
What is the unit of G?
Sir, Newton per mm.
Newton per mm. What is that you got? Critical energy release rate?
22.12, sir.
Everyone got the same number? At least two more people should confirm.
22.03 Newton per meter. we are getting.
How much? How much?
22.03 Newton per meter.
As long as it is close to 22 point something, I am fine.
Yeah, I am getting the same, sir.
Okay. So that is the critical energy release rate. What is the meaning of that? When the energy release rate reaches the critical energy release rate, that is one page. So critical energy release rate is the material property. So let us look at this particular picture. This is what we call crack resistance curve, or R is the crack resistance, G is your energy release rate. Now let us look at this fellow. Let us look at the brittle phenyl. So let us say this R resistance is like your critical energy release rate. If you look at the previous energy release rate equation, your A, as you increase the A, energy release rate is increasing for a given P, isn't it? So the way that the curve drawn is correct, not correct, because it may not be linear. The point is, if it is a brittle material, the energy release rate G increases with increase in crack length. But the moment it crosses the resistance of the material, that is your critical energy release rate in some sense, then failure happens, right? If that means this is your critical crack length. However, if you take a ductile material, suppose if you are applying a load sigma 1, corresponding to load sigma 1, right? Corresponding to the load sigma 1, your G versus A varies like this. Okay? Similarly, if you increase sigma 2, the G varies like that. If you increase sigma 3, the G varies like that. And now, your resistance to the material, if it is a material is ductile material, the resistance to crack propagation also increases as a function of crack length. Let us say you have a initial crack length of A naught, and at that time you have some crack resistance, right? Now, if you apply a stress of sigma 1, all right, and then the crack length currently is A naught, but because you are applying sigma 1, at that time resistance is this much and G is also this much, the crack will not grow. But if you apply a stress of sigma 2, right? If you are applying sigma 2, the sigma 2 curve is cutting the resistance curve here. That means the crack will extend from A0 to A1 and then stop. Now, if you apply a higher load such that this curve, G curve, becomes tangential to the resistance curve, then what happens? The crack will grow from A0 to A2, because A2 is the corresponding tangential point, in a stable manner. After that, up to here, what is happening? The resistance is lower than your energy release rate. So that means the crack is going to grow from A0 to A2. And after that, you see that the slope is much higher, and hence this catastrophically grows. So that is what happens when your material increases its resistance as a function of crack length. But in a brittle material, there is no such thing. So the moment you reach the critical crack length, G is going to be much larger and the material will not resist any crack anymore. It will chip through suddenly through the material. You will have a sudden failure. Okay, so this resistance curve, so the condition for unstable crack growth is that your G should be larger than R. So here you can see this R is larger than G, but if crack has to be unstable, then the dG by dA should be also greater than dR by dA. That means the slope of this line should be larger than the slope of this line. That happens in this region. That is why the crack grows unstable. Okay, so I think with that I'll stop here. In the next class, I think 8th you have an exam. All the very best for your exam. And we will meet next week, and there we will try to complete the fracture mechanics and start working on the fatigue failure theory. Okay, you have any questions on this?
Professor, one thing, like, can you please give the solutions for the assignment, like, in the later end is also fine.
Okay, for first assignment, I will try to send you the solutions by tomorrow. Okay, second
Sure,
assignments I will not give because
Yeah,
I
yeah,
need to spend.
that's
Yeah,
okay.
okay.
That's okay. Yeah,
Bye.
thank you.
Bye. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, thank you, sir.